Okay, so we want to start with learning a little bit about crystal plasticity and structure of DAMASK today. Okay, um, if you will try to see what, if you will try to understand what crystal plasticity is, so basically what we do is, in generally in metals we have a crystal structure. In most of the metals it is cubic, so face-centered cubic or body-centered cubic. And if I draw that here, it looks something like this, right? And for example, if it is face-centered cubic crystal structure, then we will have atoms on all corners and all on all faces, and then there will be some planes that are more densely packed, right? In case of face-centered cubic crystal structures, it is this 111 plane. I can draw any of the 111 planes, but generally, if I draw it like this, it will be this plane here, right? For example, one of these planes. So it will in total have um, um, 1, 2, 3, 4, 4 on the above, 4 on the bottom. So we total have 12 slip planes. So we total have 12 slip planes, right? Um, and then all these slip planes have all these planes have 12 possible slip directions, right? I think the number of slip planes was different, but we have in one plane we have 12 slip directions. So in for each direction, so for example, for for this direction, one in the positive side, one in the negative side. In this direction, one in the positive side, one in the negative side. In this direction, one in the positive side and one in the negative side. And these are the planes usually where the slip initiates, and then it moves on until it is saturated, and then the and then so on. How will we know if this slip um, starts or does not start? Mhm. Mhm. So what we generally have is we have Schmidt law, right, which states that there is a resolved um, shear stress on any slip system, right? Which means if we have a crystal oriented like this in overall big material, and we are applying load like this, first we have to resolve it on this slip system, right? So there is this slip system is at a certain angle, and we are applying load at a certain angle. There will be an angle between it, right? And then this resolved force is then further divided in its components. For example, there is this one direction which it can propagate in, there is this other direction that it can propagate in, and then there is this third direction it can propagate in, right? So then there is this angle of this resolved force with respect to, for example, slip direction, right? And resolved shear stress is cos of theta, cos of um, um, cos of phi into um, I think it is total stress that we apply. So it is the stress that we totally apply. And that from here we get this resolved shear stress, right? Now, if this resolved shear stress is greater than critical shear stress that is required for a plane to slip, if it is greater than this, if this condition is achieved, then the slip will take place. But if it is not achieved, the slip will not take place, right? And basically, what we are doing what we do in crystal plasticity is we try to apply a global force on our material, and we try to resolve that force on. According to this, we try to find out the resolved shear stress components of all the crystals and all the slip systems, and see if slip in a certain slip if it satisfies criterias in any of the crystals, if this criteria is satisfied in any of the systems, right? If it is, we apply a certain slip. It takes place according to a certain there is a certain velocity gradient attached to it, so it takes place according to there is a certain velocity attached to it. So how fast will this slip take place? And then there is this hardening rule. So when will this slip stop taking place? We also have defined them generally for every slip system, and according to that the slip takes place, which means it is relatively easy to understand on a single crystal structure. Still complicated because we have many slip systems, slip planes, and on them, on each of them, 1, 2, 3, 4, 5, 6 slip systems, right? It will be even more complicated when we have single grain with different orientations, or if we have multiple grains with random orientations. We want to divide this overall force on every slip plane, see which slip system would fulfill this criteria, and then we apply this loading. Basically, this is what crystal plasticity is. So we want to define a crystal orientation. We want to check when the plastic criteria will be reached, and then when does it dissolve. How does it resolve? How does it propagate? When does it stop? So this is all the mathematics that goes behind it. Okay. If we talk about the mathematics a little bit, generally we have the overall deformation gradient of our system, which can be resolved into the elastic part and the plastic part. Oh, right. The elastic part is basically depending on, you can see I do not know the equations by heart. You can see the equation. So this part depends on the um, stiffness matrix of the material, which is a nine component elastic stiffness matrix of the material. So this part depends on that, and then the plastic part depends on the material that can plastically deform, and then generally it is sum of all slip systems and one to whatever. So it can be, so I don't know, whatever. Um, and and it is basically this what we have written here. So it is um, total stress into the M versus N, the cross product of this, which is primarily this matrix. So set of all the slip systems that can take place, and set of all the slip directions that can take place. So a cross product of this multiplied by this, and the total amount of slip is this, basically the plastic deformation gradient that we have talked about. Um, basically we combine the both and we get a total deformation gradient, which is a combination of elastic part and the plastic part. Now in this plastic part, we can either define a very simple plastic deformation criteria, for example, a phenomenological law where we only find this kind of deformation, or we can have a more sophisticated or complicated plastic deformation law, where, for example, we define it on a more intrinsic level of what is the initial dislocation density, how the dislocations are moving, how they are tangled with each other, and then in the end, how hardening takes place, right? And we can also have combination of plastic deformation laws, for example, slip with twinning, or slip with phase transformation, or slip with twinning and phase transformation, right? So combination of all of them. So generally, the deformation is combination of elastic part and the plastic part. So far, so good. And this is basically what we are trying to do, run or simulate in using any crystal plasticity software. Here we are taking example of, for example, DAMASK. You can use Abacus with your own subroutine. So you can define the flow rules and then you can use Abacus. Um, there are other crystal plasticity models available out there. People have written their own scripts and models, and they're also using them, for example, for for any of such simulations. So the basic idea or understanding is this, right? To simulate that, now we will come towards a little bit of the practical side. To simulate that, we need to tell the simulation software. So any simulation software requires three parts or three components, right? What are those? Preprocessor, processor, and post-processor. Okay, so in pre-processing, we define everything that is required for simulation. These are all the inputs, right? Processing is how these equations will be solved. So the mathematical basis or the solver part of it. So how these equations will be solved, how frequently, how much, when will we consider these equations to be solved, or when we will consider the equilibrium to be reached, and things like this. So everything related to solving these equations, right? And post-processing is basically um, um, refining the output data and presenting it in more meaningful ways or terms or graphics, let's say, right? So visualizing what has been solved and what has been stored in more meaningful way is covered in post processing. So far so good. In case of specifically in case of Damask, we can configure it in two ways, right? Now with Damask 3 we can configure it in three ways, but the version that we will talk about, that I will show you here, that I have experience with, is very similar to the new version. Just the scripts and everything is different, but generally that could be configured in two ways. We could either use Damask as a material model or material library, right? And then the processor would be a simulation software like MSC Mark or Abacus, right? Or we could use Damask to run fully resolved crystal plasticity simulations. We will talk about it, what they are later. And then the processor would be spectral solver, right? When we will talk about Damask standalone, for example, in your case or in your case, we will specifically be talking about this using Damask with spectral solver. Even if you will, when you will be using DAMASK 3, we will still be talking about using DAMASK with spectral solver. We will not talk about other processors, right? So let's focus on this. Okay, to to do processing using spectral solver, we primarily require three things to be defined. Now we are coming in the preprocessor part, right? So it depends on the processor, the preprocessor will change, and also the postprocessor will change. That is why I started from here. For spectral solver, we want to define a geometry file. Then we want to define a material file, and we want to define a load file. These are the three files that we need for DAMASK to be used with spectral solver, right? And once we will solve all these equations, the output is written in terms of a spectral out file, which is a binary file, and then we use scripts specifically to read data from this binary file and, for example, find out stress, strain, orientation, what else, in the basic results, generally this, and then we can get a lot of information that reach is there. So which slip systems activated, what was the energy of each slip system that activated, what were which crystals deformed more, which crystals deformed less. So when I say stress, strain, or orientation, basically every parameter that resulted in this as well. So these are very high level parameters, but we can obtain any information below them as well, whichever is calculated in this binary file. But generally we are more interested in looking at stress, strain, orientation change, and so on, and then we can plot it in different or multiple ways, and that is what you will see in how people present crystal plasticity data or information in more meaningful ways. Okay, so if I um, look at this is the overview of how DAMASK works, and this is basically what we want to go through step by step. Okay, any questions so far?
So for refers to preprocessors or refers to input for spectra, first define geometry or no specific order for them. For example, first geometry, then material, then load,
We
or
need these three files to run a simulation.
the order of them is not important, matters which of them,
We need these three files all
all
together.
of them needed.
Yes.
Good.
Okay, and yeah, so what I can do very nicely and what I can show you is how these three files look like. So I have this folder where I have some examples, and we can see, for example, here you will see a geometry file. It can have any name but should have extension .geom. Okay, then we have a material config file. It should have exactly this name, and then it is called material.config file. And the third file is load file. It can have any name, but then, for example, it has extension.load. Okay, so if you have these three files in a folder, and then they will contain certain data, we will talk about that now, you will be able to run simulation on this. Damask will be able to automatically see data in the .geom file, .load file, and material.config file. Okay, you should have these three files in your systems. Okay, so now let's come to learn about these files one by one, and then at the end we will talk about solver, right? So how the equations are solved and how the output is written. So let's talk about the geometry file first. If I want to define, I will start with the 2D case because I can draw it on a plane. It is easy to visualize. Okay, so if I want to define one material, one, so I'm writing here one phase, one crystal. Okay, and I have this geometry size. So I will say this geometry size. We can define any geometry size. Um, I can say this is 1 by 1. And also in the third direction, we only have one element. So when I say it is 2D, it means this direction is also 1. Okay, so basically we just have one element. Okay, so my geometry file will have address of this pixel, which will be 1. Okay, and in my geometry file we will only have address of this, so I will call this 1, and therefore my geometry will only will have here 1 in the, and then on this side I want to write the material configuration file. No, I can't. I have to use this. So in my material configuration file, I will say my, so I will say this is um, one grain has um, this and this and this configuration. It has one. The important point here is it has phase 1. So, oh, the important information here will be, I will also delete this. The important here information will be one grain has phase 1, orientation 1, and then it is homogeneity. So it is always 100%. So it is fully this one material, right? And then we have to define what is phase 1. We also have to define what is orientation 1, right? So then we will say it is 1 orientation is, let's say, so this is one cube, but it can have orientation like this, it can have orientation like this, it can have orientation like this, right? So we define this in terms of Euler angles, and for example then here we define all three Euler angles um, this this grain has to define its specific orientation, okay, with respect to my reference coordinate system. Okay, so it will have information about Euler 1, Euler 2, Euler 3, and then, so this is this information, and then for this we will have it, this phase has, so in this phase what we define is um, what is the what is the critical shear stress for its, how many slip system, which crystal orientation it has, how many slip systems it has, what is the critical shear stress for every slip system, what is the hardening rule, um, and um, and all these attributes. right? So everything, so all the attributes related to that crystal is something that we define in this phase information. These are the names or attributes that people from MPIE when they were building Damask have used, and therefore we are just using the same. And the terms get much clearer later, right? Now here we only had one phase, right? I can also have this one phase in a slightly different configuration. I can now have 10 by 10 by 1. So it is still 2D, right? So I have 10 pixels in this direction, 10 pixels in this direction, 1 pixel in the other direction, which means these are not 10 by 10, but it will look something like this, right? Now, every point here has its own address. Okay? I can I can either say this is 1 and this is 10 and this is 11 and this is 20 and so on, and then in the end this will be 100. So you can also see how Damask is reading. So it is starting from the bottom left corner and it fills this one row, then goes to the next one, then goes to the next one, and in the end finishes here.
You mean it's such as meshing? Working such as meshing?
And it is not such as meshing. It is just we are resolving that more, right? So the idea, so you will see, the idea is one uh, box now has address 1, and the next one can also have either have address 2. So we can go here and then the last one will have address 100, or if it is same material with same orientation, all of them can have address 1, right? So either I will write in my geometry file to build this, either I will write in my geometry file that this is a 10 by 10 by 1 sized RVE, right?
Yes, yes.
And it has um, this address. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on until 100. Or I can write 100 times, right? And what changes here is that if I have different addresses of each, right, then in my material file I have to write here information about every grain like I did here, right? So I will have to, in this case, either I will have to write grain 1 has phase 1, orientation 1, and 100% homogenization, and then I will have to define orientation phase of 1, right? Or if it is just one material, one crystal, I can just define this 100 times here, and then in my material file it will be quite simple. So I will only have to define one grain, one orientation, one phase, and so what happens is that um, I have to clear this. So how Damask reads this is Damask looks at your geometry file. It it sees, for example, oh, this grain has address 50, right? Then it goes, for this to understand what this point is, it goes to the material file and then sees which what is the information about grain 50, right? So somewhere here there will be information about grain 50. So I will write here grain 50, and then it will see, okay, this has phase which one, and orientation what, and from here it will understand what this point 50 is. Do you understand that?
Yes. No, one question. Like first for that, now we have one material
Hmm?
and we define it this material. Yes. Now for this, for example, I go to part 50 or phase 50 for
Hmm?
this. Now is it one needed to define 100 grains material or not? It's not needed. For example, based on the material, DAMASK find this and allocate these properties to, for example, phase 50 or no. We have 100 parts, we have to step by step, grain 1, grain 2, define all of them.
Um, let's take it. Let's take another example. It will be easier for you to understand. I want to define a material which is still 2D.
Hmm?
Okay, so it has um, 3 by 3 resolution. We are
Resolution.
calling it resolution. Okay, this means it will look like this, and this means it will look like this. Okay, what I tell you is outside, everything outside is one crystal,
Hmm.
right? With orientation 001, right? And it is steel,
Okay. Yeah.
let's say. So steel, but one crystal, everything outside. And this point is cementite,
Hmm.
and it has orientation 111. Okay, and now I have to tell this to Damask.
Hmm. No, we define it. Thomas.
How will you do that?
Hmm. I got it.
So the question is, how will you do this? Right? So what I can do is I can define. So first, what I have to do is I have to give address to each of these sections to properly resolve it. Right? So this block will have an address, this will have an address, this will have an address. Every block will have an address. Now they can either have different addresses, or there is an easier way to define them if, for example, all of these outside points will have the same attributes. What I can do is I can define this as 1, 1, 1, 1, 2, 1, 1, 1, 1. The other way of doing this was 1, 2, 3, 4, 5, 6, 7, 8, 9. Both are correct.
Yes, yes, I got it. Now for the same use and for this different.
Damask will be able to understand both, depends on how you then build your material configuration file. If I define one for all the materials that are same, it is much easier to define a material file for that, right? Because in the material file I will write grain 1 has certain phase, has certain orientation, has homogenization, has certain homogenization, and then Damask will read, okay, what is its phase? I will write all the systems, all the slip systems that can activate, what is the resolved shear stress value, what crystal orientation it has, what is the hardening rule in this, under this, right? And then I will say, okay, it has orientation in terms of Euler angles, I will define it 001. And now this information will be used for all these points where I had written 1. When Damask will reach understanding, will try to understand what 2 is, I should have here information about grain 2. I will say it has phase 2 and orientation 2. And then I will have to define phase, what phase 2 is. I will have to define which elastic stiffness matrix it has, which orientation distribution, which slip systems it has, which crystal structure it has, how they deform and so on. So I will have to define this for phase 2 as well. Right? Now imagine doing this if I rename them 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I will have to do this for all 9 points
Yeah.
in the material file, but for all these points it will be the same, right? So my material file will be very long, but if I intelligently understand all these points are same, I can give them the same address. It does not mean that the resolution is dropped, it only means that my material file is now relatively more easy to understand and see. It will make more sense a little bit later, right? um, what I want to do is I want to show you let's look at a relatively more complicated case. Okay, and then you will understand the geometry. So we are still talking about just the geometry file, right? So what I want you to write the geometry file for, I want you to write the geometry file for this is 5 by 5. Hmm? Now, this is still steel. Okay, so if I show you with mouse, so this is still steel, but it has two boundaries. Let me change the color. One is this boundary. This is 001 orientation. The other boundary is this. It has 111 orientation. Okay, and then in the middle we have these 4 points that are the other phase, right? I will also draw it with this. So this is phase 2. We will always call it phase 1, and this is phase 2 with 001 orientation, right? How will this geometry file look like?
Look like in the software.
Yeah, so how will you define its addresses? Like we discuss things here, now. How will you define its addresses?
Initially, first we define the geometry by defining the sides like in XYZ direction.
Yeah.
Then afterwards, we'll try to introduce faces. And regarding the faces, each face we select the grain boundary orientation, grain sizes,
Hmm.
Porteous angles, and
Hmm.
uh, when by selecting those data, we'll get information on the number of slip planes and slip systems available.
Yeah.
So when we club all together at once, the file which we contain in the geometry section will has the uh, entire volume, data of entire volume, which gives
how will you number? Can you write them down here? How will you number these?
Each section.
How will you number it?
Okay, like defining a specific part of the geometry file belongs to phase two. How are you telling me how to do that? Okay.
Like we discussed here.
Okay.
How will you number it?
Okay. Initially, when we are
Just
okay.
but it is not 5 by 5.
Okay.
My point of view,
Hmm?
my point of view, I think that we have to
Don't think, just draw.
just yeah.
Finished?
Yes, yes. This, in my point of view, I
Mm-hmm.
define three grains or refers to this point.
Mm-hmm.
One static grain refers to the phase one with the disorientation, one,
Mm-hmm.
one, one. Another grain define it with the same phase, it's phase one, but different orientation with
Mm-hmm.
this. And another refers to the second phase because it's completely different.
Mm-hmm.
Define this phase with this orientation.
Yeah.
In my point of view, three
Mm-hmm.
grains we can
Okay.
define.
And
Okay. From my point of view, like when you define two phases in a single system, like we need to define the volume percentage.
uh-huh.
Okay. While giving the volume fraction, then obviously the data will obviously be in the geometry file, which gives information like how much, like where exactly where different phases are located.
But we already know where the phase will be.
Okay.
We just want to explain this to the computer. So you did well. So the idea is, for example, we can define any address to this. So it will be 1 1 1 1 1 1 1 1 1 because all these points have same phase, have same um, phase and same orientation. And then because the orientation is changing here, this will be 2 2 2 2 2 2 2 2, right?
Okay.
So then we will have this, and here we will have 3 3 3 3. Why? Because in the material file we will define grain 1 has this phase, this orientation. Grain 2 has this phase, this orientation. Grain 3 has this phase, this orientation. So which shows if your orientation or phase is changing, it is better to change the address of that specific point. If not, there is no need to change that, right? And there is a reason for that. Why are we doing this? Why are we doing this? We do this because later we will have polycrystalline material structure, right? So one material with different grains. right? And we will want to tell the computer that we have polycrystalline material. So it is one material with different grains. How do we do that? We define a specific resolution. We say this is 50 by 50, let's say, which now means it has 50 boxes in this direction, 50 boxes in this direction, a total of 50 multiplied by 50, right? Which means if I just redraw this, which means it will look something like this, right? So if then this grain boundary will be resolved like this, right? And then we will say all these points that are within this are 1, all these are 2, all these are 3, all these are 4, these are 5, these are 6, right? And in my material file, I will only have to define grain 1, grain 2, grain 3, grain 4, grain 5, grain 6. Why? Although they all are steel, because they have different orientations. That is how we define a grain, right? So how do we define grains? A grain is um, a block of the material consisting of the same chemical composition, of same crystallography, but has different orientation as compared to the other one. This is how basically we define grain. And when we want to define grain for Damask, this is how we will do that. Do you understand that?
Yes, yes,
Right? And now if we will have a different phase, let's say we say, okay, this grain 3 is not steel, it is another phase. It will still have address 3, but it will also now have this address 3 does not correspond to phase 1, it corresponds to phase 2. So you have to understand how those attributes or properties or schemes are. Okay, so this is the significance of the geometry file. Understood? Any questions? Okay, I again mentioned and said that that what we do is how we write Damask geometry file is um, it starts from this end, it goes to this end. Once a line is finished, then it starts from here again, goes here, and then it starts from here, and then goes here, and then it starts from here and goes here. In case of 2D, in case of 3D, its z-axis is in the other direction, which means it will first create this um, first layer, and once this will be complete, then it will start building.
Exactly.
So it will first create this layer, and once this layer will be complete, then it will automatically start from this corner again for this next layer. And once this layer will complete, it will automatically start from this corner of the third layer. Is that clear? Now if I want to draw a 3 by 3 by 3 geometry. By 3 by 3 by 3 geometry, I mean like this, and then like this, and then like this, and then also like this, and also like this. Okay, so this is a 3 by 3 geometry, right? In the middle of this geometry, this middle block is another phase, but all the others are phase. So this everything is phase one. This is the middle block is phase 2, and everything has orientation 0, 0, 1. How will you define a geometry file for this? Just write it down. You don't have to draw this, just write down how the geometry file will look like. Now we want to write the addresses with this in mind.
Okay. While defining, since we are going from block 1, 2, 3, likewise,
Mm.
so if you want uh, to define a block here with a different phase, we'll start defining the blocks phases like with 1, 1, 1, 1, 1, 1, 1, 1, goes on till here.
Mm.
From here, we'll give uh, the y direction for this block.
This one
Yeah, for that block.
is not on the surface, so it is the middle one. So middle one here. So in this layer, the middle layer,
Mhm.
the middle block. So it will be somewhere here
Okay, yeah.
in the middle of the cube.
Uh, so at so okay, so it's not.
Can you write these 111 here, like you would tell the like you would tell abacus? So
First row.
yeah, then the next layer will be.
Uh,
So you've written 111. This 111 is here,
yeah.
and then
The middle block it comes over here.
no, but this comes later. So first you have to just you're starting from here.
Okay. So the second, while defining the second row, if the phases are same, then we'll define it as 111 as
Yeah.
usually. And
Then
uh, for the third row, if at all the phases are same, we'll define 111.
okay.
But in between,
No. So
sorry.
this is okay.
Okay.
Now, and in my point of view, now as I told you, first go such as a row, and after that finished means one, two, three, finished, and after that the start goes to the z directions.
Mm-hmm.
In my point of
So
view,
then you
this
define. Then you start defining exactly like this. Then you start defining the next layer.
yeah,
And
So yeah,
what will that
the
be like?
next layer will be like this direction. So
No, it is still the same.
mhm.
So just assume that now you have removed this and now we are just looking at this layer now. And in this layer, what will this look like? So if I draw this here, if I break it down into three layers, the top layer looks like this. The second layer looks like this. This is the block that I was talking about. And then the third layer looks like this. And if I will put this at the back of this and I will put this at the back of this, I will have this.
Okay.
Do
Okay.
you understand that?
Yes.
So we're going from a 2D problem to a 3D problem.
Okay.
So this was
So
this,
for each, yeah.
right? And now if you will define this, it will automatically go at the back. How do you define this?
It's like one, 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 one,
No.
two.
Why are you writing upwards?
Sorry.
Why are you writing up? So you're writing addresses on
Yeah,
them.
yeah, yeah, yeah.
Do not. So that is what I said. Do not write addresses. Write like how Damask will read it.
Okay.
one, one, one.
Damask reads it from here like this, and then like this, and then like this. So it will be,
So it starts with the first block,
yeah,
which is phase one.
which one?
I
This
think
one.
this one, yeah.
Okay.
And the second one is phase, yeah.
Yeah.
Third one is also phase,
Yeah.
and fourth one will also be
Why
phase.
are you writing it above here?
So because it's reading like as going
No,
straight.
but you have to write it in, like Damask would read it.
Okay.
You have to write it down here.
Oh, okay, okay.
So,
So one again, and here we define this block as phase two,
okay.
and another one is one, and following by the same.
Yeah, and then this one.
And this one it goes by as the all blocks are same phases. We'll be defining all the blocks as the same phase category.
Now write it here all together.
Yeah. So
No, just continue writing it down like this.
oh, okay.
Okay, good. Okay, and one thing that I missed telling you is how will Damask know where to fit all these ones and twos? Right? In the beginning of the geometry file, you will tell Damask, right, that this is a geometry file that is 3 by 3 by 3, right? So this is something that you define in the beginning. What is the size of my geometry? And once you will define this, it does not matter if you write 111 and then in the next line 111. Even if you will write all these ones in one line, it would automatically know that it is a 3 by 3 file. So it will take 1 2 3. It will assign them 1 1 1, and then even if 111s are written here, it will automatically read for the next ones 111. It will automatically read for the next ones 111, so on, right? And then when your 2 is coming here, it will automatically, once it will define this, then it would automatically go to the next line, and then it will say 111. Okay, this is now 2 1 1 1 1, and then 111 111 111. So if I write this, I can also write like 111 111 111 111
Two,
121
one,
111, and then just in the next line. And Damask will still make the same geometry file out of this information. Why? Because we define in the beginning that it is a 3 by 3 by 3 file. Do you understand
yes,
that?
yes.
Yes, I got it.
Okay, so this is how the geometry file is written, and Damask reads it like this. Okay, now we want to see an example of what does a real geometry file look like. It looks something like this. So there is always information on the top. It says 6 header, which means start. So this is always, it is a must. So it means there are 6 lines of header, right? So 1 2 3 4 5 6. Okay, excluding this line, there are 6 header lines: 1 2 3 4 5 6. That means the geometry file actually starting from here. Okay, now what is written in the header? So this is the command that we use to create this geometry file. That is what is written in the header. Now another important thing that is written here in the header is grid, right? And this is 5 by 5 by 5 file, right? So grid is written as A, 5B, 5C, 5, and this is what we are defining here, right?
Okay, okay.
So now you can see that it is a 5 by 5 by 5 file. Okay, and then there is information about
One
size.
question. 5 by 5 or 3 by 3, like how many number of faces we can define in a geometry file? It doesn't matter.
As many as you want,
Okay.
right? But we will come to that later. So now you will see that in this file it is a 5 by 5 by 5 file, which means it is 5 in X, 5 boxes in X, 5 boxes in Y, 5 in Z, which means so if you will see here 1 2 3 4 5, right? So if I start reading the file from here, 1 2 3 4 5, so this is the first layer.
Mm-hmm.
And how many it should have?
5.
5,
Yeah.
right? So the second one, the third one, the fourth one,
Okay. Total
and
5.
the fifth one.
Yeah.
Do you understand that?
Yes.
And now you will also understand what does 1 5 4 5 3 5 mean.
Faces.
These are just, no, these are just addresses of every box.
Okay.
We don't know if they are different phases, we don't know if they are different orientations. It is just addresses of these points. This is how Damask reads a geometry file. Now Damask will also have the same question. What does 4 or 5 mean? Right? And other points that I want to tell you are homogenization, defining microstructure, defining origin and size are all required according to the script or according to how Damask is built, right? But in our cases, we will not be dealing with any of them. We will only, so this line is not needed at all. We can just remove it and make this header as 5. It will still work all fine. This line is also not needed. We can completely remove it, make this header smaller. It will still work fine. These these three lines are needed, right? So where is the origin of this geometry? What is the size of this geometry? But we can always define this size as cubic. So it is 1:1:1. So this is always the ratio. It it just controls how we'll be able to how we will see or visualize the geometry. It has nothing to do with any of its characteristics or changes. So this is 1:1:1. This means the x ratio is equal to y ratio is equal to z ratio. So this 5 by 5 by 5 file will look cubic to us, right? It does not change any calculations. It does not change any characteristics, just visuals. And then the important point that we discussed and you understood is what is the grid size and how that grid is then explained.
Explains. One more thing, for each 5 by 5 matrix, the address file will be same, like the 11151 will be same, or it will be differ.
It depends on how what your material is,
Okay.
right? So this is what we are trying to understand, that for, that later if I will say now you have this material, tell it to Damask what you have, you will be able to build this file for your own material or microstructure.
So another thing, before selecting the grid, do we need to define faces then select the volume? Like initial, like if do we need to define the faces, like uh, 1115, these are the addresses, but afterwards like we'll be giving the meaning to it, like okay, the one this address and this
That
is
is
like the face.
that is what we do in the material file, and that is what we
Okay.
are going to go to next. Okay,
Okay.
so here one is just address, and Damask will have same question, what does one mean? And to explain that, we have to go to the material file. We cannot define that here.
Yes, got it.
Mhm. Now, one question happened for me. Now, now in this part, the resolution define 5 by 5. Yeah. Now we can define by ourselves or depends on the material, because we can say, for example, for me 10 10 10 10, or if one person says that 3 3 3,
Yeah.
all of it will be different.
Yes. Yes. So if you will look at an example, uh, I will just look at completely different example. Um, so you can look at this geometry file. It will be quite large, right? So it is now 150 by 112 by 1, right? So if I say understand and try to make sense of this, it will be very hard for you to do that. And therefore, we are looking at smaller files to make sense of how DAMASK reads and understands it. But generally, our real files look something like this. And here, if I open this file, it is very easy for me to understand what does this line mean, what are these lines, from where do I have to see its size, what does this signify, how many microstructures, so how many addresses this file totally has, and then what is written here, right? But the principle is same that we have discussed before. Of course, this depends on what your material is, what you're trying to explain to Damask,
Yes, I got it.
right? But the principle will remain the same. This will change. Now, again, 168, 3 are just the addresses. What do they mean? We have to go to the material file. I will not look at the material file here because it will be more complicated. I will go back to our, again, the the example that we were looking at. Practice simple, and I will try to open material.config file. Okay, so now if there were, so I will open them side by side. Now if there was, how many numbers do you see? 1, 2, 3, 4, 5, right? So you have 5 numbers here. 1, 2, 3, 4, 5, right? So I automatically expect that in the material file we will have grain 1, grain 2, grain 3, grain 4, grain 5. So we will have information about all these 5. Let's look at them. Let's look at the, oh, not this one. Let's look at the material config file, right? So we have grain 1, grain 2, grain 3, grain 4, grain 5. Is that okay?
Yeah.
Right? And now all these grains have information. So all of them, see there, all of them have information phase 1, phase 1, phase 1, phase 1, phase 1. Right? Which means it is a single phase material. It
Yes.
only has single
Single
phase.
phase. Yes.
But what is the difference between 1, 2, 3, 4, 5? It is texture 1, texture 2, texture 3, texture 4, texture 5, which is basically orientation, and which is defined here for grain 1. So texture 1 means this, texture 2 means this, texture 3 means this, texture 4 is this, texture 5 is this, right? And you will see all these angles in the Euler space are different, which means this is single phase material with 5 different grains. Each grain has different orientation, and which orientation that is defined by,
Defined here.
defined here, right? And now we want to see information about phase, right? They all have single phase, which means it is just one material, which basically means it will have same crystal structure, it will have same number of slip systems, it will have same um, uh, critical shear stress, and so on, and hardening rule and so on. What will only change is how, when we apply the total force, how it is resolved on each plane. Maybe for the same material, because it is resolved better, this slip system will activate and the other one will not, right? And this is what crystal plasticity is. And for this phase information, this is where our phase is defined, right? So our phase has elastic part and the plastic part. So elasticity is Hooke's, plasticity is phenomenological power law. This is where we call in the libraries. For the elastic part, so we are defining then this as a body centered cubic crystal structure. These are the number of slip systems, 12, 12, total of 24 slip systems. Then the number of twin systems are 0. We can also delete that, it will not matter. And then these are the elastic parameters that are necessary to define this. And then these are the plastic parameters, right, that are necessary to define this, right? And this is the output of total shear if we want to obtain output from here. So which shear took place on which slip system. If we want to take that output, we can do that. Otherwise, we do not need it. We can completely ignore this. Okay, so this is how the material file is written. The requirement is it has certain sections. So texture should be defined with a specific format under texture. The grain numbers should be defined with the under microstructure with specific structure. Um, and under phase, we define the phase information, right? And then under crystalline, we define the outputs that we want or expect. So this is where we are already now looking at here, right? So we are already looking at the solver. So in the material file, we are defining which material file we are already defining. We are already assigning certain tasks to the solver. So which attributes should it save um, when solving the equations, right? And then in the beginning we have homogenization scheme, which means when we apply the external force, how is it resolved on every grain? So generally we have isostrain, which means it is equally divided on all the grains and orientations. So this is true for so this is correct and true for bulk materials, and where the slip systems are more active than the grain boundaries. So in those cases, isostrain is a very reasonable homogenization scheme. So how do I divide this force on every individual grain? Just resolve it with respect to the size of every grain, right? So this is the specific format of the material file. We should have this, and now the important thing here is um, to understand what is written here, right? So if you define two phases here, then you should have information about the second phase in this section as well, right? And if all these grains only have a single orientation, then either you can just define grain 1 and define all those as 1, and here will be just one line, and here we will also have just one line, right? Or if we have multiple grains, then primarily there is something different in every grain, and we want to see what is the difference, and for that difference we want to define specific terms and keys, right? Now the good thing is you mostly do not have to write these files yourself. You will get these blocks, right? So what are the phase information here? We will talk about it later. So usually you get this information from DAMASK libraries, from people who have already published their work and so on. This is something that when you construct a geometry, it automatically creates this with that. So you just copy and paste it here. So whenever you create a geometry file for something, Damask any software will not just give you these 1 2 3 4 5s. It will also give you a separate information about what 1 is, what 2 is, what 3 is. What you have to do is you just have to copy that, know that I need this information, copy that information, put it in the material file, so Damask can correlate it with this. We cannot make big geometry files without any automation or that help. It will be very hard to write them manually, or we will make a lot of mistakes.
Yeah, that's what I'm trying to do.
Yeah, sure.
Yeah, so you don't have to write them manually, but you have to fully understand what they mean and what do they signify, so you can handle this data by yourself. Okay, the third file that we have to talk about is the load file. Okay, Um, load file is relatively easy and simple if you have basic idea about how finite element simulations um, um, work. So in the load file, I will go down here and then I will start writing again. In the load file, we have um, deformation matrix, stress matrix, um, time increment. Okay, so we have a 9 by 9 deformation matrix, a 9 by 9 stress matrix, a time scaler in seconds, and increment value. We will talk about this. So deformation matrix is how do you want to apply deformation,
Uh,
right? So for example, I say I want to apply deformation in x direction, right? So it is not deformation, it is deformation velocity. So it is not just deformation, it is deformation velocity, right? So deformation velocity matrix, stress um, matrix, and then time and increment. So I say I want to apply one deformation.
X direction. I mean,
Yeah, so it is basically a component. So basically, this is deformation in x direction. This is deformation in x y direction. This is x z direction. This is deformation in y x direction. This is in deformation in y direction primarily, and then y z direction, and then so on, right? So zx, zy, and z, right? So if I say I want to apply deformation in this direction, what I usually do is I make hysterics. So so because if I apply deformation in certain direction, there will be negative deformation in the other directions. I don't know that. So I will just say I don't know that, so I will write my hysterics. But I do not want to apply shear, so what I will always do is I will write here 0, 0, 0, 0, 0, 0. Okay, so now this is 1. How much deformation is this will depend on for how much time this deformation is applied, right? So if my time is 10 seconds, this means this deformation will be 1 multiplied by 10. If my time is 1000 seconds, this will be 1 multiplied by 1000, right? And for stress, usually what I do is, what I want always to say is stress, whenever I'm controlling something, stress in that direction is um, uh, to be found out. No, stress in that direction is always 0, right? So there should be no stress in these directions. So stress should always be resolved. So this is my equilibrium condition. And then for the other directions, it should always be found out. And I think I also want to calculate it for the stress. I'm not sure, but it is usually like this. Okay, if I show you an actual load file, it looks something like this, right? So it is written in just one line. You can also write it in separate lines like we talked about, but this is basically first component, second component, space second component, space third component, space the other component, space the other components, right? And in the stress matrix, it is written something like this, and then you will see time 2, increments 10, frequency 2.
Passing of increments to means.
We've not reached there, but you understand this is how it is written. Okay, so this is understood. So there was also a static here. We also want to calculate stress here, right? Now, um, um, about increments. So increments are, I want to go, I will just remove this. I want to apply this deformation velocity for 1 second. I want to apply one deformation velocity for 1 second. Um, the question is, do I want to just calculate this 1 point, or do I want to calculate 3 or 4 or 5 points between these 2 points?
Yeah, I get it.
Right? And this is the number of increments.
Yeah.
So should it be 1? Should it be 10? Or should it be 100?
Depends.
What difference does it make? It discretizes my calculations. Right? So this is point A, this is point B. I want to go from here to here, right? I can jump in one step, or I can jump until here, then jump until here, then jump until here, and then jump until here, and then jump until here, right? Because when you plug in very large values into the equation, sometimes it is not for the computer, because it has to make all the calculations, it has to find an equilibrium position. Sometimes it is not possible for the computer to find a very good equilibrium. Theoretically it should be able to do that, but when you're dividing very big numbers with very small quantities, especially in terms of metrics, when you are trying to find approximate solutions, sometimes it happens that you will not be able to find a possible solution. If you divide relatively smaller numbers with relatively bigger numbers, you might be able to find a solution. Once you find a solution, you're already at this point. Now it is much easier to jump a little bit upwards and a little bit upwards, and this is where we discretize our equations again. So what is the reason of doing this? We are helping our solver reach the desired calculations and equilibrium faster, so we can get our desired results. So you will see that we are already doing everything basically for our solver, right? So this is where we are helping our solver. What does this frequency do at the end? This frequency do at the end? Maybe I need a lot of calculations to reach this time 1, but I do not want to save all of them. So I tell my solver, only save the 10th step in my computer, but please do this in 10 steps so you reach a converged solution. And this is where that frequency comes in. So frequency 2 means it will only save the every second frame to my computer and not all the frames. Okay? So this is basically the configuration of all these three files. If you have these, if you can construct these three files for your for any material, if you have these in your system, you can just run a basic DAMASK simulation and you will get some results. So what you will get is a binary file like this, like a spectral out file, but you will not be able to open this file. If I open this with, oh, it will look something like this, right? And then what I have to do is I have to run scripts to read data out of a meaningful, useful data out of this file so that I can make plots, I can show it in meaningful ways. But this is all about our preprocessor and processor. And yeah, so that's about it. What I will do is I will end this session now.